Hey guys, welcome to another exciting C++ tutorial. In today's tutorial, we'll be making a simple neural network from scratch using no third-party libraries and a little bit of mathematical concepts like matrix, linear algebra, determinants and stuff like that. And yeah, let's jump into coding. So first of all, let's create a simple header file called matrix.h, and all this header file will do is it will contain a class called matrix, which will help us in doing all the matrix related calculations, all the linear algebra related calculations. So we will create a class called matrix and it will have a constructor. Let's make all fields public for now. Okay, and it will have a constructor called matrix, which will take first let's include a vector, and also let's include math.h or cmath. I think these two things will do. So all that our matrix will require is let's say uint32 underscore t. This stands for unsigned integer of 32-bit. So rows, columns, and uint32 underscore t rows. Okay, so this is the constructor of a matrix. It will take the columns and the rows, and we will have some public fields, public. So we'll have some public fields to store these values. So uint32 underscore t row calls and 32 underscore t underscore rows, and a vector std vector of floats to hold all the values present in our matrix, and we will call this vals. Okay, so first of all, let's initialize our matrix using an initializer list. So our calls will have the value of calls, and our rows will have the value of rows. It's raining outside, so there are some little noises of thunders, just ignore them. And vals as an empty vector. Okay, so we will just say underscore vals dot resize, and we will set the size of the matrix to be calls times rows, and also we'll set the default value to be 0, just like that. So now we need to access the values present in a matrix, so we will define a function called at. So float at, and it will have column number and the row number. So uint32 underscore t call and uint32 underscore t row. Okay. And we'll just simply return underscore vals, and the value that we will return is our row number times the number of columns that we have, so underscore calls, and we'll offset it with call. So this is it, and it will return the number that is at number row and number column index of our matrix. Just think this as a 2D array. If it's a 2D array, then if the 2D array is compacted in a 1D array, this will be the index correspondent to that 2D index. This is the 2D index, and this whole thing is the 1D index. Now the next thing that we need to do is we need to have a function that will multiply two matrices. So, and it will return also a matrix. So we will say matrix, and we'll call this function multiply, and this function, this multiply function, it will take another matrix. We'll take it by reference. We'll call this target, because we will not be changing our target by any means. So what we can do is we can also say const matrix reference target, like this. And now first of all, we need to include a header file called cassert C assert, because we need to have some assertions that must be satisfied, and the assertion is very simple. We will assert that our number of columns in our original matrix is equals to the number of rows in our target matrix. So target dot rows. Okay, this is the assertion we are going to make, and if it's true, then we will create another matrix. We will call this output, and it will have the number of rows equals to our original matrix that we are multiplying with, and the number of columns will be equal to the targets. So we will just pass here target dot column that calls and our matrix, so just underscore rows, or you can say these dot these arrow rows, whatever. Now we need to fill this output matrix using standard matrix multiplication. If you don't know what is standard matrix multiplication, I highly suggest you to look into some matrix maths, but let's just do it here. For event y is equals to 0, y is less than our number of rows, so output dot underscore rows y plus plus, and then we will inside here, this will be event underscore t, sorry, and here we will say event 32 underscore t. We'll have x here, and x is less than output dot underscore calls x plus plus. So we move through all the elements of our output, and we will first of all we have a output. We'll first of all have a float that will store our value float. We will call this result and set it to 0, and then what we will do is we will loop through another loop. So event 32 underscore t, k is equals to 0, k is less than underscore calls k plus plus. We will just say result plus equals to at k comma y times target dot at x comma k. Okay, we can say output dot at, and actually what I think is we need a reference here, because with the reference we can modify it as well, otherwise it will just return the value. So we can now say output dot at y comma x, not y comma x, but output dot at x comma y is equals to result result. Now we'll check this later. So this is typically how the matrix multiplication function looks like. I think it's because of the const. Now we have defined multiply, we also need to define add. So matrix add, and we will have two matrix. One is our original matrix and one is the target. So matrix target, reference target, because if the matrix is so big we need to avoid as many copies as possible. Okay, and add is very simple. First of all we need to assert that both the matrix has the same dimensions. So underscore rows is equals to target dot underscore rows, and underscore calls is equals to target dot underscore calls. Okay, this is the simple assertion we will make, and we will have our these two loops just as they look, nothing so fancy. And all we are going to do, okay, and let's just move these things a little bit, and all we need to do is simply add the values at that particular row and call. So we'll say output dot at x comma y is equals to at x comma y. This is our original matrix value present in our matrix, and target dot at x comma y, at x comma y. Okay, like that. So with that we have our output, and we need to return our output in both cases. So return output, and here also turn return output, and here also we will return output, and this m will be capital. Okay, so we have a function for addition and we have a function for multiplication. Now we also need to multiply scalar values with our matrix. So I will define another function here, just here. I will just copy this here and just create another function. I will call this multiply scalar. It will take a float value, a scalar value, float, let's say s, and this is pretty straightforward. All we are going to do is we are going to remove this. We are going to say output y comma x is equals x comma y is equals to at x comma y times our scalar, and then we will return the output. So it's as simple as that. We can also define an add scalar function. We don't need this assertion in here. It will be same as our original matrix. So underscore calls underscore rows, just like here. Okay, and yeah, I can call this as underscore calls underscore rows. Okay, like that. Okay, so we have multiply scalar, and we also need add scalar. So let's quickly copy and paste it here. We're doing a lot of copy and pasting so first. So we will call this add scalar, and the only difference is that instead of multiplying with the scalar, we will just add the scalar value here. Okay, so we have these things. We have multiply scalar, add scalar, and we need to subtract the matrices also. So we will just define a function that can give us a negative matrix, which will have the exact negative values of our original matrix. So we can call that function negative. So we will call matrix negative, and all it will do just here matrix negative, and all it will do is it will also perform the same operation here. Let's just move these things a little. Okay, and all it will do is output dot at y comma x will be the negative value of the original value. So we have negative here, we have add scalar, add, multiply scalar, multiply, and the last thing we need to do is to have a way to transpose our matrix. So we'll say matrix transpose, transpose, and transposing is actually very simple. We need to create a matrix with the reverse dimension. So rows will become column and column will become row. So matrix output will have the reversed column and rows. So for rows and underscore calls, like that, and then we'll just set the values. So we will copy our greatest loop here, just a little bit of formatting. Don't know why it's doing like this. Okay, This is good. So we will copy this thing once again. Okay, there isn't many change. Most of the matrix multiplication and operations are just looping through all the columns and rows and doing stuffs. So we will say y is less than rows, output dot rows. Let's just say output here, output, yeah. And let's just say this rows and calls, and what we will do is we will say output dot at the reverse location, so y comma x is equals to at x comma y. Okay, this is all about the matrix class that we need, and now we can jump into our neural network. So we will create another class. So let's add another item. So we'll call this neural network. So NEURL neural network, like that, dot h. So first of all, we need our matrix class. So let's include that. Include matrix dot h. Now I am using double quotes because this is a header file that I have written. It's not provided by the standard C++ libraries, and we already have other things here. For random values, I think I need to include stdio, stdlib, sorry, stdlib. Now we can use the modern random number generation, but I don't think that's necessary for this simple tutorial, so I will just skip on that. So we'll say class neural network, or simple neural network. Let's say SIMP, simple neural network. And so let's say we have, just let's comment this area here. We have two inputs. Okay, we have two inputs here. This is one input and this is another input. So the inputs that we have will go to two neurons. Let's say two starting neurons, and these two starting neurons will belong to the first layer of our matrix, of our neural network, which we will call layer number 1. Now let's say we have another layer here called layer number 2, and it will have 3 neurons. And then let's say we have such n number of layers here, and then finally we will have something like this, which will be our layer number n, and which will be the last layer of our neural network, and that will return us our output. So we'll say output, and this we can say in for input. Now as we can see in this particular diagram, the elements that are present in one layer, they will be transmitted to the next layer, and for every neuron present in one layer, it will have a connection to all the neurons that are present in the second layer. So for these two layers, for layer number 1 and layer number 2, if this is 1 0 and 1 1, and for determining this is the 0th neuron of the first layer and this is the first neuron of the second layer, just let's move these things. So here on layer number 2, if this is 2 0 2 1 and 2 2, so this is the 0th neuron of second layer, and this is the first neuron of second layer, and this is the second neuron of second layer. We will have a connection between 1 0 and 2 0, and the same will we will have a connection between 1 0 and 2 1, and we will have a connection between 1 0 and 2 2. The same thing 1 0 and 2 2. and the same thing will be applicable for 1 1 also. 1 1 will also have all the connections with 2 0, 2 1 and 2 2. So what we end up with is 6 connections. We will have 6 connections, and those 6 connections can be represented as a matrix of dimension 3 cross 2 or 2 cross 3. We will see it when we implement how we can design that thing. Both ways is fine, just how you represent it determines how you use it. So we'll have a 3 cross 2 matrix which will have all these connections between all these two neurons. So we will have a total number of 6 connections here, and the thing will go on for each layer. So every layer they have some neurons which are densely connected to the next layer. This is particularly a dense network that we are designing, and for every connection we will have a correspondent weight. Okay, so the thing that our connection will represent is a weight, and this weight, it will determine how much one neuron influences the other. So let's say the weights that we have here for our neurons for these two layers 1 and 2 are W 1, 20, 10, 20, and W 10, 21, and W 10, 22. The same thing you can write it here like W 11, 20, W 11, 21, and W 11, 22. So this will actually be our weight matrix. We will call this our weight matrix. This matrix right here, we will call this our weight matrix, and the value at next layer. So let's say our value at 2 0 will be equals to the value of 1 0 multiplied with the correspondent value of W 10 and 20 plus the value at 1 1 multiplied with the correspondent weight of W 11 and 20, the particular collections, and so on. So this is how we will determine the propagated value, the value that is going from here to here, using this formula, just the summation of all the values multiplied with the correspondent weight of the connection, and this multiplication will be easier if we use matrices. And the next thing what we will do is we will have something called as an activation function. So activate, let's call this activate, and we will pass this whole multiplication value to here to get the activated value, and that will be the value of the next layer, and like this the value will be transferred to the next layer, and that value will be transferred to the next layer, and so on. Okay, so for these 3 neurons we will have such 3 pairs of calculation. For 2 1 and 2 2 we will have like this 2 1, 2 1 and 2 2, and as you can see, as the number of neurons increases, the number of calculations also increases. So for that, what we will do is we will use our matrix to save all the values, and also we will use matrix multiplications and additions to calculate all these correspondent values. Okay, now let's create our neural network. So we will have something, so let's declare a public field, and the first thing that we will have is the topology of our neural network. So std vector of uint32 underscore t called topology underscore topo logy, and what this topology suggests is the number of neurons at each layer. So let's as example, if we have 3 neurons, then 3 neurons at first layer, then 2 neurons at second layer, and 1 neuron at the last layer, our topology will contain these values like 3, 2 and 1. Okay, so we'll have this topology here. The next thing is our weights for all the connections. We will call this weight matrices. So std vector of matrix, we will call this weight matrices. So underscore WEIGST weight matrices, and also we will have our values stored in a matrix, the values that are being propagated to all the matrices here, these values 1 0 1 1 and 2 0 2 1 2 2, and we will call these matrices as value matrices. The difference between the weight matrices and the value matrices is that our value matrices, as we can see here, our value matrices, as we see here, have a single column. Okay, we have different rows for the number of elements, number of neurons in the layer is equal to the number of rows in our value matrices, and the number of column of our value matrix is always 1. Okay, so you can also consider it as a tensor in TensorFlow. And our weight matrices here, it will be of size m cross n, where the m and n is the size of our of the two layers which have all the connections. Total number of connections is m cross n, as you can see here. Okay, so that being done, what we can do is we can create our neural network. So we can say public here, and we can create our constructor. So simple neural network, and our constructor will take a topology. So vector of uint32 underscore t, we will call this topology, and let's first of all let's say std vector here. Okay, std colon vector. Okay, just like that, and let's initialize our topology to have the value of our topology. Okay, this topology. Now we need to also initialize our value matrices and weight matrices. So underscore weight matrices will be initialized to a default value, underscore value matrices will be initialized to a default value, and we will have two additional matrices here. I am just declaring them right here, so I don't need to cover them again. One is our bias matrix, BIAS, bias matrices, and the bias matrices represents to the, let me be clear, the bias matrix will have the same dimension as our value matrices, and it will be just a little value, like say B10 for the first B20 for our first matrix, and so on. Okay, the main job of the bias matrix, so just let's say B20 here. Okay, so the main job of our bias matrix is that we'll have a little bit of deviation from this calculation, and it will make ourselves easy to have a proper calculation in less number of training cycles because of this bias. Okay, so we'll have this bias matrix also, this bias values, and whenever we are going to start training our neural network, we will have to define the margin of error that we're going to modify. Like we have some error and we want to modify. We are not going to modify all the things at the same time. We're going to modify a little by little, and that thing is often called as the learning rate. So we'll say float underscore learning rate, and we will just pass this learning rate in our constructor here. So float learning rate. For some reasons I am having a lot of spelling mistakes, and let's this learning rate will be a very small number. Let's say for example 0.1 here. Okay, and this will determine how much changes we will do to our neural networks whenever we are going to train our neural network and modify the weights to suit our needed result. So here let's just initialize these two things. So bias matrices to one empty matrix, and let's say underscore learning rate to our learning rate. Okay, so now we have all these things initialized. We can now construct our neural network here. So first things first, we will initialize our weights, values and bias matrices depending on the topology. So we'll look through the topology. We'll say for uint32 underscore t I equals to 0, I is less than topology dot size I plus plus. Okay, and what we will do is we will first of all define our weight matrix. So let's say matrix weight matrix, and the weight matrix of each layer will have the number of columns equals to the next layer. So topology I plus 1, the number of columns of the next layer, and also we will not look through all the neurons, but all the layers of the topology, but we will exclude the last one because we are accessing it with +1. So we will put a -1 here, and here we will have topology I. Okay, so this will take care of this will take the next row and the next layer. If these things are considered as layer, it will take the next layer, this number 2 layer, and it will take the previous layer. Like if I is equals to 1, it will take this layer and this layer, and then it will create this matrix. But in this case I am just creating this matrix in a column order. Here I have represented it as a row order to save some time, but here I am just creating it as column order. Okay, no much difference. Now what we will do is we need to initialize these values of our weight matrices. Let's just create a function that will look through all the values of a matrix and do some stuffs. Okay, so we can have another header file included here. So include functional, so that we can pass some TIONAL functional. We can pass some functions to our matrix, and let's call this function. So we'll call this void apply function, and it will take a std function, function of which will return a float value, and we'll take a float. So const float reference, and we'll call this function as func. Okay, like this. Okay, and what apply function will do is it will do the same thing that we have all done previously. We will take a matrix here, from here, yank, and P. Okay, so it will do this. It will take the function and it will apply the function to all the elements of our matrix. So func, because all the elements are float, so we will just call func on all the values, and with that we'll construct our new output. So it will be obviously a matrix written, so matrix matrix. Okay, so with that now we can apply a function to all the values of our matrix simultaneously, and we will do that actually. So we already have our weight matrices right here. We will save our new weight matrices as a randomly initialized weight matrix. So let's say weight matrix equals to weight matrix dot apply function, and it will take a float, just make it here, it will take an arrow function which returns a floats and takes a float. So const const float reference f, I guess, and all it will do is it will return a float number between 0 and 1. And to do that we will first of all, if float cast the value returned by rand to float, and then we will divide it by rand max. Okay, and this will give us a value between 0 and 1, and the new values will be stored in our weight matrix. It's as simple as that. Okay, and here we have included stdlib for the availability of rand and rand max. Now that our weight matrix have been initialized here, what we can do is we can push our weight matrix to our weight matrices. So we'll say underscore weight matrices dot push back our weight matrix, just like that. Okay, now the same thing is going to be happening with our bias matrix. So just let me quickly do it here once again. So matrix bias matrix, and our bias matrix will have the size of topology i+1, and it will have, as I said, a single row. Okay, here we are looking it as column, but here we are doing it as a row, just the reverse of this. Okay, so that our matrix looks like this, actually like this. So it looks kind of like a vector. Okay, that's why I am doing this. Otherwise our matrix would be looking like this, and I don't want to do that. Okay, so that's why I am just reversing this. This is the reason, nothing else, just for the pleasure of your eye. If you want to do things like this in the reverse order, you can also do it. It doesn't really matter. Now that we have our bias matrix, we also need to apply our do the same thing to our bias matrix. So let's just quickly copy this function, and let's say bias matrix bias matrix is equals to bias matrix dot apply function, and let's just paste the function here. It's really that simple. Okay, just a little bit of formatting here, make things look good. Okay, so we have our randomly initialized bias matrix. All we need to do now is just push the values to our bias matrix. So underscore bias matrices dot push back our bias matrix. Bias matrix. So we have already initialized our weight matrix and our bias matrix. All it's remaining is our value matrix, right? Obviously bias matrix. Okay, so the last thing that we need to do is initialize our value matrices. So we'll say value matrices dot resize, resize, and we will just resize it as our topology. So topology dot size. So value matrix will have the number of layers that is correspondent to our topology. If our topology has 3 layers, then our value matrices will have 3 vectors of 3 matrices. Each matrix will contain one set of values corresponding to that layer. Okay, once again, these values will be represented horizontally, not vertically. So that's, I think, all about initialization. We don't need to initialize anything. Now what we need to do is we need to design the main working of our neural network, that is the propagation of the values from one layer to next layer, and this thing is often called as feed forward. So we will call this function feed forward. We will say bool feed forward, okay, and this feed forward function, it will take a input. So std vector of input, vector of float, fl float, called input. Okay, and the only thing that we need to check is that the size of our input is equals to the number of neurons present in our first layer. Okay, so in our topology, the first value will be equals to the size of the input. So we will say input dot size if input dot size is not equals to our topology 0, then we will return false. So this is the only condition check that we need, and if this condition succeeds, then we will simply return true. Now we will go from one layer to the next layer, but first of all, let's create a matrix out of these inputs. So we will say our first input matrix, so we will say matrix values, and it will have the size of input dot size, and it will have a single row, and the number of columns will be input dot size. So it will just convert our input to a matrix called values, nothing else. Now what we will do is we will assign the values. So for uint 32 underscore what I am typing t, I is equals to 0, I is less than input dot size I plus plus, and all we will do is we will say values dot underscore vals I, because it's a single row matrix, it will be just like input I. Okay, so that's all for initializing our input matrix and creating this values matrix. Okay, this values matrix is actually our input matrix. Now we will look through all the layers and propagate the values to next layer, and it's actually very easy. So we'll say feed forward to next layers. So let's say for uint 32 underscore t, I is equals to 0, I is less than the number of connections is represented by our weight matrices. So I will say I is less than underscore weight matrices dot size. You can also say topology minus topology dot size minus 1, it doesn't really matter, I plus plus, or you can use value matrices or whatever. Just we need one less here. If we see, if we have n number of layers, the number of connection weights will be n minus 1. So for n layers we have to loop through n minus 1 times. Okay, so we are using weight matrices because weight matrix actually is one less than the size of weight matrices is one less than the size of our topology. Okay, so what we will do in our feed forward, it's very simple. We will say underscore value matrices I is equals to values. Okay, so for the first layer, for the zeroth layer, first of all we will define that our first value matrix is 0 is equals to the values, and then what we will say, we will create values for our next layer. So we will say values equals to values dot multiply, and we will multiply with our weight matrices. So weight matrices I, it's as simple as that, and it will take care of multiplying all the values and creating our new values. It's actually looking very simple than this complex explanation, right? And also we need to add the bias values. So values values is equals to values dot add underscore bias matrices I. Okay, so we'll add the bias with the multiplied values with the inputs, and then we will apply our activation function, this activation function here. Now let's quickly have an activation function. There are different kinds of activation functions. There are so many activation functions. For a simple scenario, a very common activation function is called sigmoid. So we'll declare sigmoid, 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 and it will take a value x, and it will all it will do is it will return 1.0 over 1 plus e to the power minus x. So exp stands for e to the power, and here minus x. Okay, so 1 over 1 plus e to the power minus x, this is also known as sigmoid. You can search sigmoid in internet and you will find sigmoid. And this sigmoid function, it has a very interesting derivative. We also need that, so I will just declare it here, inline float d sigmoid. D stands for derivative, and it will take the value of a sigmoid function. And the most beautiful thing about the derivative of a sigmoid function is that it's actually the value of the sigmoid function. So return x times 1 minus the value of the sigmoid function. Okay, so it's just this. Isn't this beautiful? Now if sigmoid this x, it's actually the value returned by the sigmoid function. It's not the x here, but the output of this sigmoid function is this x here, and the d sigmoid is actually very simple. It's just the value into 1 minus the value returned by the sigmoid function. So with that, we can now apply our sigmoid function to all values. So we will say values is equals to values dot apply function sigmoid. Okay, and that will take care of all the complex mathematics in feed forward. And this value will be used next time for the next layer. Then the value will be updated, and then the values will be used in next layer, and every time before updating the value we will attach that value to the value matrix of that correspondent layer. And the output layer being our last layer, all we need to say here is value matrices underscore value matrices, okay, dot weight matrices dot size. So the last layer size, the last topological layer, will have the value of our value matrices. And this is all about feed forward. It's very straightforward. First of all, we convert our input to a matrix of a value matrix. Then for each connection layer, what we assign the values first, and then we recalculate the value by multiplying the weight matrices, adding the bias matrices, and applying the activation function. Okay, as simple as that. Now this will this works for having an output of our layer, and we have already achieved a system that works as a neural network. The only thing is that we don't exactly know what the values of the weight matrices and bias matrices should be, because in the constructor we just assign the weights and the biases with some random values, but in reality these things are not random values. These are adjusted by a procedure called training that neural network. And how we adjust it? It's very simple. We first of all determine the error. Okay, we feed forward through the neural network. Feed forward. We feed forward through the neural network, and this feed forwarding, it returns us a result or a output. Now we have a targeted output. Okay, so we have a target output. Let's say our target output is 1, and we got an output of 0.5, target, and we got an output of 0.5. So we will have a error which will be equals to our target minus error, target minus our output. So we needed the value of 1, but we got 0.5, so we had a 0.5 of error. Now what we will do is we will have our derivative of our error with respect to all the weights. So we can say ddw with respect to all the weights, the partial derivatives with respect to all the weights, and those derivatives will give us the direction which will be actually either a positive value or a negative value, depending on which we will decide whether we need to reduce the weight or we need to increase the weight, so that the next time the error is minimized. This concept of mathematics of reducing our value or increasing our value so that the error is minimized this minimization, this is actually minimization. Okay, minimization of error, minimization of error, and this is also known as finding the minima. In this case we're just interested in the local minima that we can find, not the global minima, and this minima will have a error that is almost equal to 0. Okay, so our target is that we will minimize this error so that the error is 0, and to do that we will modify our weights and our biases depending on the error via taking the derivative to find the direction where the weight should, whether the weight should be added or removed, and then we will increase the weight or remove the weight with a small amount which is determined by our learning rate, which is here we are having a default value of 0.1. okay, somewhere here we have defined it as 0.1. You can also change this, it doesn't really matter. So what we will do, we will now define a function to do all these things, and we will call this thing backpropagate, because we will start from our output layer this time and we will go back to the input layer one by one. Okay, not the input layer but the first layer after the input. Okay, so that all the weights can be adjusted depending on the previous weights and the previously calculated errors. It's actually pretty simple, then it actually is pretty simple than how it sounds. So we'll say bool backpropagate. Let's check the value name here. Let's make this small f. Okay, so backpropagate, and it will take our output. So we will say std vector of float. We will call this target output, and with the target output we will backpropagate. So first things first, we need to check the dimensions. So if target output dot size is not equals to underscore topology dot back, what we will do is we will return false. You can also generate an simple error and print it to the console if you like, else everything is done correctly, so we will just return true. So now what we will do is, first of all, we will create a error matrix with our targets. So we will call this matrix error, which will have the size of our target. So target output dot size, size comma 1, and then what we will do is we will set the values of the error dot vals dot underscore vals to our target matrix, target output OUT PUT. You can also do the same thing here. Okay, I'm not changing it, but you can also just simply assign in feed forward, instead of going through loop and assigning one by one input, you can just say values dot vals equals to input. Okay, just like this. And now what you can do, what we need to do is we need to subtract the output achieved by our original neural network. Now the output is nothing but the last layer of our value matrix. So we will say error, let's make it plural because we will have a lot of neurons and they will have a lot of errors. So errors dot add, and here we will say underscore value matrices dot back, so the last matrix dot negative, and this is equivalent to subtracting. So errors equals to errors dot add. Take this away from here, the compiler is making an stupid error. I don't know what's the problem. So let's say matrix subtraction matrix is equals to underscore values dot back dot negative. Okay, and we will just replace this with sub, and yeah, the compiler is not making any error. It doesn't make any sense. So we'll just loop through for uint32 underscore t I equals to weight what the hell is this, weight matrices dot size -1, so the last layer of the weight matrices, and until I is greater than or equals to 0 we will reduce I. Okay, so we'll go from back to front, that is why it's called back propagation. We are going back from back to front. First of all, we need to calculate the previous error. So matrix prev errors, okay, which is equals to errors dot multiply, and we will multiply with the weight matrix but in reverse order. So we will say errors dot multiply underscore weight matrices dot matrices dot I dot transpose. Okay, so we'll multiply it in reverse order, and obviously we don't need to give this thing, and for some reason I don't know, it's producing this stupid error. So we just need to declare the transpose matrix outside. So we'll say trans is equals to this thing, okay. So trans equals to weight matrix dot transpose, and we just delete this line here, give the bracket here, and we'll say multiply trans. Okay, matrix are we outside the class? No, I don't think so. So we'll say matrix D output is equals to underscore value matrices I plus 1, because we have one more value matrix, dot apply function, and here we will, oh, this will be trans, trans. Okay, so apply function, and inside apply function we will put our d sigmoid. So all the values, all the sigmoid values, they will be derivative, and so we have the derivative of the output, this derivative of the output here, this ddw, this derivative of the output here. We have calculated the error by subtracting the output from the target, and then we have found the derivative. Okay, so this is the derivative, the output of the output. And now that we have the derivative, we need to multiply the derivative with the correspondent errors to find the delta errors. So we will say matrix gradient. This gradient means that the gradient says is either positive or negative. We can see here the gradient is either positive or negative, defining whether I should increase the weight or decrease the weight. So we will say matrix gradient is equals to gradients. There are multiple gradients, so we will just say matrix gradients is equals to underscore error, not underscore errors. I'm doing a lot of spelling mistake today. Errors dot, and we need to element wise multiply. I haven't really defined an element wise multiply. Just quickly let me define an element wise multiplication. Element wise multiplication is very straightforward. Just let's do it here. So let's copy this and let's paste it here. We'll call this element wise multiply. So multiply elements, and it will take a target. So matrix reference target, target, and all we need to do, the matrix will be same as this. All we'll do is we'll say at xy times target dot at xy. Okay, this is all about element wise multiplication, same as addition, nothing that surprising. Okay, and also we can check this condition here for having a error proof code. Okay, so now we have this. We can say errors dot multiply element, and we will multiply it with our derivative value, so d outputs. Okay, like that. So now we have the gradients that we needed. Now we can say gradients dot gradients equals to gradients dot multiply scalar, and we will multiply it with the learning rate, underscore learning rate, and this will give us the actual values that we need to modify. So now we have that, we can say that matrix weight gradients, just a second, my PC is running low on battery. Okay, so weight matrices weight gradients, sorry, matrix weight gradients, the gradients of the weights are equals to underscore value matrices I dot transpose dot multiply with gradients. It sounds a little weird. Let me explain what we are doing. We have found these delta errors, and then we have find let's call this d error, and then we have multiplied our d error with our learning rate. We have multiplied our d error with our learning rate. Let's capitalize this, learning rate. And now we need to adjust our weights according to our error. And how we will do that? We will simply take the transpose of our current matrices, our current value matrix. So what we of our current value matrix, and which will convert the row into column. So if our value matrix is like this, it will convert the matrix like this. Okay, and so because the matrix is now transposed, we can easily multiply this transposed matrix with our gradient, or in this case our d error. Okay, so we can easily multiply this with our d error, and this will be our delta weights. So dw, our delta weight will be equals to this whole multiplication stuff. And when we have our delta weight, we will say our weight is equals to weight plus our dw. Now dw can be a positive or negative, or a negative value, and it will adjust our weight according to it. Okay, nothing else. It's actually very simple. So underscore weight matrix says I is equals to underscore weight matrices I dot add this weight gradients. You can also say d weights, whatever you prefer. Okay, and we also need to do the same thing for our bias matrices. So we'll say bias matrices I is equals to, as it's just a single column matrix, so what we need to do, we can say by bi underscore bias bias matrices I dot add gradient. Gradients. Okay, so it's as simple as that. And now we just set the errors to the previous error, and we keep on looping through the loop. So we'll say just errors is equals to previous errors, and hopefully that's all about creating a neural network. So we have our feed forward function, we have our backpropagate function for training, and feed forward function for feeding the neural network. The last thing we need is a function that will return our values. So we'll just say std vector of float, we'll say get prediction, and here what we will do is we will simply return underscore value matrices dot back the last value matrix, its values underscore values. Okay, and with that we have successfully created our neural network class. Now let's include this neural network in our main.cpp and test out whether this neural network is actually working. So what we will do is we will design something called as a XOR test, which you can't do unless you have multiple neurons. Okay, so we'll include IO stream here for our IO input output, and we also include our neural network class. So quotation neural network, so we also include our neural network class like this. Now Let's just first quickly create our topology. So we'll say std vector of let's say uint 32 underscore t topology. Let's say our first layer will it has two inputs and we have one outputs x and y, and for x1 and x2, and for that we are finding y, and inside we have three neurons as our hidden layer. Okay, this is a simple topology. It can be as complex as you like, but we are just using a simple topology to test things out. Now we say std, not std, sorry, simple neural network. I will call this nn, and we will initialize this with topology and a learning rate, let's say 0.1. Okay, now we need a set of outputs. So std vector of std vector of float, we will call this target inputs, and it has two values. Okay, so let's quickly assign those values, 0.0 f and 0.0 f. So it's for 0 0, for 1 0, for 0 1, let's say for 1 1, for 1 0, and for 0 1. Okay, now the same thing we will define the output here. So we copy this, we paste it here, we put a semicolon here, we'll call this target outputs. So target outputs, and it's actually very simple. For XOR, the logic is that if, let's just delete these things. So if the two values are different, then the output is 1, and if the two values is different, the output is same. So for the first two cases, the output will be 0, and for the second two cases, the output will be 1. Okay, now let's define an epoch, the number of times we want to train our neural network. So epoch, and let's set it to a very large number like this. Okay, it's C++, so I don't think it will take a lot of time. So let's just say std zeroth training training started. Okay, like that. Actually it will be like this, training started. And now we look through our epoch. So we'll say for uint 32 underscore t I equals to 0, I is less than epoch I plus plus, and here it's very simple. We will take a random index. So uint 32 underscore t index equals to rand modulus 4, because we have 4 inputs. So we will take a random input and we will feed forward that input. So feed forward target inputs index, and then we will cross check with our target outputs. So target outputs index, and this will be called backpropagate. Okay, as simple as that. And this is all about training. So we can say here that our training is completed. So training completed. Now we can loop through each input and we can check if the values are given correctly. So we will say for auto input belongs to target inputs, we will feed forward our input and then we will take our predictions out. So auto predictions equals to neural network dot get predictions. This is a vector of float, nothing else. Get predictions. And now that we have our predictions, we can say that let's print out something. So cout input 0, then a comma, then input 1, then something like an arrow for the output, and let's give some spaces here, and then our predictions 0 because our predictions has only one value at the output. Okay, and after that let's end the line. So end here, and we will append std in front of cout and end line, and then return 0, RET0. And that's all about our test of our neural network. If we run this simulation now, we get an error saying that no default constructor is available. So just quickly make a default constructor. Let's copy this, let's paste it here, and in this case we will just take all these things out. This is our default constructor. We'll set columns to we'll set columns to 0, not here. We'll set columns to 0, we'll set rows to 0, and we'll set the values to empty. And as for values goes, it will have nothing, so we don't even need this resize operation here. I guess that should be enough for our default constructor, I guess. So now if we run this program, so I paused it a little bit and to find the error, and as you can see it's saying vector subscript out of bound, and it's happening here because of this unsigned int, because unsigned int can never go below 0, so this actually failing the test. So all we need to do is we need to convert this to int. Okay, and now if I run this program, we can see that the training has been started, and it's gonna take some time because we're looking through a lot of values here. Okay, we're looking for around 1 lakh times or 10 million times, so it's going to take a little time, not so much. It's going to do a lot of matrix multiplications here, so let's just wait. And now as we can see, our neural network has been successfully trained, and according to our input for 0 0 it's giving us a 0.0. For 1 1 it's also giving us 0.0. For 1 0 it's giving us a 0.9, and also for 0 1 it's giving us a 0.9. so these predictions are quite accurate according to the training, and as you can see our neural network is actually working properly. Now if you have enjoyed this video or learned something from this video, I highly suggest that you like this video. It motivates me a lot to make these kinds of video. If you have any questions, you can write them down in the comment section, and please consider subscribing this channel for such contents in future. And thanks for everything. Bye.